since yesterday. Yeah. I have more classes this weekend. Okay. Oh yeah, that'd be great. But, yeah. I think my plan was just to kind of look at distributed systems literature and see if anything. Yes. Are you good? Yes. Okay, so let's start. Alright, so a couple of quick announcements, the usual ones from last time. So homework 4 is due on Monday. So this is mostly homework on probabilistic algorithms. And yeah, basically tests the things you should know, Markov inequality and difference inequality, stuff like this. And yeah, and it's due this next Monday. Okay, and as most of you know, project meetings are going on. I think almost all of you are meeting. A couple of outliers, but apart from that, it's all good. Okay, so yeah, and if you still haven't decided on your project, which is maybe true for like 4 or 5 people that I think with that in that status, so please just send an email as quickly as possible. Okay. All right. So that's about the project. Okay, so today the goal of today is to essentially give like a short summary of everything we've seen in randomized algorithms so far, and kind of move on to our next topic, okay, which is optimization. And I thought that this would be useful, just a quick reminder of what we've been saying, given that we've been doing it for like 3 or 4 weeks. So what did we look at, right? So we said that using randomness in algorithms can have a lot of benefits sometimes. And one of the key things was that somehow if you have problems in which there are many good solutions, but it's kind of difficult to pinpoint one, then that's when randomness is used. And you might ask, what kind of situations does this happen? We saw a bunch of situations. And one of the, in some sense, the striking examples was, suppose you're given like some 2 large polynomials that have like large number of coefficients and so on, and in multiple variables, that x is actually a vector of variables. Then you know that if p is not equal to x, then p is not equal to x for a typical choice of x, okay, for random choice of x. Okay, and that is one of the striking examples of randomized algorithms. Okay, so like maybe you, for many deterministic algorithms, it could be. I mean, in fact, this is one of the problems for which we don't know very good deterministic algorithms. So I'll come to that in a little bit. And right, and one thing we found is that usually randomized algorithms have some probability of failure. Okay? And failure could mean multiple things. It could mean, for instance, that the answer that's output is not the right one. It could also mean that the running time is larger than you would like it to be. Okay, so that is, and in that case, you might want to bound these kind of probabilities. Right, so this is one of the typical features of the analysis. And the other thing we keep analyzing is the expected running time, okay, or expected performance behavior, or something like this. And we did this in a couple of examples. We did this for quicksort in class. You're doing it for median selection in your homework. And both analyses are very similar. And so this is based on this idea of writing what we call a probabilistic recurrence. Random recurrence. And, so this is kind of a specialized idea. It doesn't work in too many problems, but it works for these couple of nice examples. Right. And one of the things that showed up always in our analysis of randomized algorithm were these notion of random variables. Okay, random variables are usually, we looked at real value random variables, where these are just some measuring the outcome of some probabilistic process. So that's what we call a random variable. And they have some distribution, and we kept computing the expectations, and we also had this nice property of linearity of expectation. So we said that if you take two random variables, the expectation of the sum is the sum of the expectations. Okay, so that's what linearity was. Alright, so, and then we saw a couple of very useful examples. Okay, so the first one was balls and bins. You have a bunch of balls that hash randomly to a collection of bins, and we analyze various things like what is the distribution of the bins and how many bins are empty and so on. And this is useful because this is often used in the analysis of hashing. And many of your projects involve some clever use of randomization, some kind of estimation method. Another very powerful use of randomness is sampling. Okay? So you want to estimate certain quantities. We saw this question of estimating the winner of an election by just taking samples. And there, it wasn't quite, I mean, so there defining the random variables, computing the expectation was easy enough. But the key thing was to argue that that the estimates that you get are always close to their expectation. So, and for this we needed this notion of concentration of random variables. Okay, so we wanted statements of the kind, you had x which was a random variable, x is close to the expected value of x with probability at least, I don't know, 99%. Okay, so you wanted meta statements of this kind. Okay, so the difference between x and expected value of x is not too large with high probability. Okay, so that's the kind of statement we want. And one of the results we saw, although I realized I didn't quite phrase it like this in the last class, it came out from the calculation, but I didn't emphasize the final result as much. Is the following. Okay, so if you want to estimate a 0-1 outcome. Okay, so you have a population, everybody has a 0 or a 1. You want to estimate the fraction of ones. Okay. Then if you want to estimate the fraction to an additive error of plus minus s, you need something like 1 by s square samples if you want a probability of, let's say, 3/4. Of being correct. So this was a consequence of the calculation last time, but I didn't explicitly state it. But I like this way of seeing it because it kind of gives you this clean dependence between the error and the number of samples you need. Okay. So if you are estimating just like a 0-1 quantity and you want to estimate the fraction of ones, and let's say your fraction of ones was, let's say 0.4 was your true fraction of ones. And you wanted to estimate this number 0.4 up to a plus minus epsilon accuracy. Okay. Then you need something like 1 over epsilon squared samples. Okay. And yeah, this just comes out of the Chebyshev calculation that we saw last time. Okay. But in practice, sometimes you are faced with this question: oh, okay, I want to estimate some quantity to a certain error. How many samples do I need? Right? And instead of doing the whole calculation every time, this is a good heuristic to keep in mind. Okay? And in general, it would be something like if you want an error of plus minus s, you would have some variance divided by s squared or something. Okay, but this again, as I said, follows from Chebyshev. All right. So that's something in about sampling. And in both, yeah. So in general, as I was saying, this concentration of random variables plays an important role. Okay? And so the meta result in this whole area of concentration. So this is actually a big area by itself in probability. Okay, so there are like books about concentration inequalities and stuff. So what the meta result there is, random variables don't deviate too much from the expectation. And what do you mean by too much? What do you mean by much? Here is the question. Okay, and this depends on the random variable, of course, as you might expect. And one basic inequality is Markov's inequality. It says that if you have non-negative random variables, then the probability that you are is more than some p, hence expectation. It's less than 1 by p. And so this is easy statement, but it's a very useful statement. And the other thing we saw is that for random variables, the notion of standard deviation is also very useful. Okay, and this is, at least let me define the standard deviation. Its square is the variance. Okay, so the standard deviation is the square root of expected value of x minus the mean. Okay. So in some sense, you are asking, you're looking at this new random variable, which is the deviation from its expectation. You're looking at the deviation squared, and you're looking at the root mean squared. Okay. So that's the standard deviation. Okay. And Chebyshev's inequality is, again we said it's a simple application of Markov. It says that the probability that x minus the expected value of x is more than, so yeah, let's call this quantity sigma. One thing to note is that for certain random variables, the standard deviation could be infinite. Okay, so these are called heavy-tailed random variables. So I don't know if some of you have heard of it. So some of these quantities may not actually be defined. Okay, so the variance could be infinite and so forth. Okay, so but let's not worry about that. So Chebyshev's inequality says the probability that a random variable, the absolute value of this difference, okay, is more than p sigma is less than 1 by p sigma. Okay. And this is true for many random variables. Okay, so the probability is more than p sigma is, it's true whenever this sigma is well defined. So this is a simple statement. And we said that for if your x is actually a sum of independent random variables, then you can get much better bounds. Okay, so and one of the things we saw was the Chernoff bound last time, where essentially you could bound this probability by e to the minus p squared. There's a few other assumptions, but I didn't really state them. But if you had, but these are ordinarily true. Okay, so, alright, so this is something about concentration. So any thoughts or questions on this? So, this is a quick recap of things we've been seeing. So, right, so I wanted to end with like a couple of questions that we don't have answers to. Okay, so Well, the first question is there this? So we've always been assuming that that you can sample and you get some truly random bits, right? And you could ask, is there such a thing like true randomness, right? Like are there sources of random bits in the world, right? So and this is an answer question which we don't quite know the answer, right? So you could ask, how do computers generate random bits? Right? Does any of you know how, like, say, random number generators work?
At the base level, they need to collect some other sort of entropy, so they would often be like mathematical timings or sizes or something.
Yeah, but in many languages, if you fix a seed, the whole sequence is usually determined, right? So random number generation is an industry by itself. Okay, so there's a lot of work on these kind of things, and we don't have a definitive way of generating random numbers. Okay, so as you're saying, very often even the most sophisticated random number generators try to use some outside source. Okay, like they measure some CPU heat levels or something like this, or they measure some network layer properties, something like this, and with the hope that that is random. Okay, so now, right, so you could ask, okay, but is that really random? And we don't know the answer. And some people say, oh, okay, if I take pi and expand it out enough, then the digits I get are like truly random. Okay, and there's no way of certifying this one way or the other. Okay. I mean, so this is, think about it, it's a ridiculous statement because they are the digits of pi, they are what they are, right? So it's not random at all, based on how you look at it. But if you use them as inputs to any random number generator, it works perfectly fine. Okay, so I mean, you wouldn't be able to tell by just looking at the sequence. You did not know they came from pi, that they are, that they have some structure. So, so there is this whole meta question of is there true randomness? And luckily for algorithm design, at least my personal view is that these questions don't matter so much because often when you're designing an algorithm, unless somehow these random bits uh, they gang up together so that they are bad for this particular input, your algorithm will still run fine. Okay, so somehow if if you imagine like an adversary generating random bits, if the adversary is oblivious to your input, then typically in algorithms they can't mess you up. Okay, so like it's still like whatever bits they get usually still work. Okay. So I mean, as long as they satisfy some reasonable problem. Okay, so there's we don't know a good answer to this, but people still study randomized algorithms because you don't often run into these cases where where somehow the source of random bits is correlated with your inputs. So yeah, one interesting thing here is that in like the 1940s and stuff, there used to be books published. Like, and do you guys know about this? Yeah, so there's like a table of random numbers. Like, and so it would be like this book with just a bunch of digits. And the idea was that you could use these to, like a substrings of these as random. So for whatever purposes you need. So yeah, so now we have more sophisticated. So that's so this we don't know. So the other very big theoretical question is, can randomness help answer truly difficult problems? We saw that it could help in some situations like these identity testing and there are some simple primality testing algorithms and so on. But the question is, can they actually help you solve some truly difficult problem? And this again we don't know. Okay, so for all we know so far, like there is this thing called RP, which is randomized polynomial time algorithms. So this is what is called a complexity class. We'll see what those are towards the end of the course. Those of you who know, this is a complexity class. These are problems that have randomized polynomial time algorithms. That is it. Randomized polynomial time algorithms. And P is, of course, problems that admit polynomial time algorithms. Okay, and one of the questions we don't know is P equal to RT? So this we don't know. Some people believe the answer is yes. Some people believe, actually, many people believe it is yes. I think. Okay, so there is this whole community called de-randomization around de-randomization, and that's so the idea there is you take a randomized algorithm and you try to remove the randomness from it. So, or reduce the seed size to so small that you can then try all possible seeds or something. Okay, so that's this whole field called de-randomization. Okay, but whether useful or not, randomness usually helps us get simple enough algorithms. So that's why people in practice are always interested in randomized algorithms. And definitely we know that even though it may not help solve truly hard problems, we know that it can help you solve problems faster. Okay, so that one can efficiently. Alright, so those are some general, like the context you should have about probabilistic algorithms. Okay, alright, so that's this, right? So let's now move on to our next topic, okay, which is optimization. Okay, so what comes to mind when you think of optimization?
Unrolling loops.
Interesting. Okay, not an answer I would have thought. Yeah. What do you mean by that?
Unrolling for loops. So that you just not use a loop, instead just
Well, that's like
write out.
some code optimization of sorts. Okay. Interesting. Okay. Anything else? Grading descent. Yeah, that's another thing. Yeah. So whenever, yeah, for machine learning people, optimization is synonymous with grading descent, right? So yeah. Life in general. Yeah, life in general, right? So that's the other thing you could say. Okay. Yeah.
Same category of stuff that I use genetic algorithms as.
Oh, okay. Yeah, it's interesting. Yesterday also I met somebody who suggested genetic algorithms for something else. Okay.
I'm thinking of the optimization class, trying to minimize the function
Okay. So there's a theorist in the audience if you get that answer, right? So he's saying, yeah, you have some objective function, you have some constraints, and you want to optimize some. Right? So this is the general formulation. Okay? So this is what you will see also. The constraints and you will optimize. Okay, so this is, yeah, so these are all very good answers. And often, so I'm surprised I didn't get this answer, but you also should be thinking of like these operations research type people, right? There's all these like scheduling, there's railway scheduling, stuff like this. They are the people who started working on optimization. Okay, so yeah, maybe people don't think about these things, but like airlines and so forth. Yeah.
Can you be related to time? Nice.
Yeah, like I was just, yeah, it's highly general, right? I just wanted to know what you guys think of when you think of optimization. Yeah, so what do you have in mind? Yeah.
Optimize the time.
Okay, yeah, that's like life in general kind of thing. Yeah. Okay. Yeah, so this is a very general topic. Okay, so you can capture many problems with optimization. Okay, and part of what we will do. And so in general, you can think of optimization often as the way Benway was mentioning, which is you have a bunch of variables, and these variables are supposed to take values in some domain. Okay, so think of the domain as being like Boolean numbers, Boolean, okay, 0, 1 value, and 0, 1, and you want to, and you have some objective function usually, and that we denote by f of x. Okay, so this is called the objective function. And you often have constraints as well. Okay. And these, I'm just writing them as, so these need not be any polynomials or something, and sometimes like b equal to 0, less than 0, right? So, but you have some constraints of this kind. Okay, so whenever you think of like a typical optimization problem, if you try to formalize it enough, you should be able to bring it down to something of this kind. Okay, so you've got to identify what are the things I should be optimizing for. Those are your variables. Okay, and what, I mean, are there some constraints that they should be satisfying? And in terms of these variables, what is the quantity that I want to? So these are the three things that that we want to understand when we're talking about optimization. Yeah, if you think about like many, I mean, general optimization problems, you can often phrase them like this. Okay, so this will be the structure of optimization problems you think of. Okay, and this is a very meta problem. You can phrase several other problems as this one. Now, and by phrasing it, what we mean is that a solution to this can be used to obtain a solution to the original problem, and it will be the optimum solution to whatever you want. Alright, so that's that. So one question you should ask yourself now is why do we care so much about phrasing problems as optimization problems? Right? So yeah, any comments? Yeah. Yeah, so people have thought a lot about how to solve these kind of formulations for various kinds of f, various kinds of domains, various kinds of constraints, and so on. Okay? And there are existing libraries that can solve these kind of problems for many classes of these ones. Okay? So this is the reason you might want to phrase problems as optimization problems when you face something in practice, because there are established techniques for doing this. So we'll see a couple of those, but yeah, so that's the general reason you would want to phrase them. Okay, so there's decades of research on how to solve this problem. And sometimes this would be better than trying to come up with like a algorithm from scratch for your problem. And this is the reason you might want to phrase it. And sometimes, and for some problems, we don't know how to solve it without phrasing it as optimization. So anyway, so that's some reason as to why you would want to do this. And hopefully we'll see some concrete examples where this viewpoint makes life a lot easier. So in fact, maybe I should give the spoiler at this point, but so it turns out that flows are one of these examples. Like if you remember, our algorithm for flows was very clever. Okay? But it turns out you can phrase it very naturally as an optimization problem. We can see it today. And then if you assume that, okay, there's some black box that solves this problem, you can just, plug in that black box and you get an algorithm for flows. Okay, without going through this complicated thing, without trying to argue about its optimality and stuff like that. Okay. So that's the reason we try to formulate problems as optimization. Alright. So let's with that motivation, which is motivation enough, let's try to see how you would formalize a bunch of problems that we know in terms of optimizing. Okay, so let me write down the problem itself. I should put these on the next slide. But okay, so what is the problem? The problem is you have n jobs and you've got m machines. Okay, and these machines, think of m as being 5 or 10, okay, something small. And your goal is assign jobs to machines. Okay, so sorry, I forgot to mention. So each job has some length, which is L1, L2, up to Ln. And assign jobs to machines such that the total length of job assigned to any given machine is less than or equal to t for some given t. So your input also consists of some number t. So you're given some length block. Okay? So this is like the total amount of time you have or something. And you want to assign each job to one of the machines so that the total length of jobs, so they all finish before time t. So that's your goal. And your goal is to minimize, is to do this for a given t. Okay? And ideally your goal would be to minimize the t. So the t is as small. So often this is also phrased as saying minimize the maximum load. The maximum load is like the load of a machine is the total length of the job it gets, and you want to minimize the maximum. Okay, so that's another way of phrasing this. All right, so this is a clean problem, right? So is the problem kind of clear to everybody? You have a bunch of jobs, and think of this as trying to assign these jobs to machines so that the maximum load is as small as possible. So now, how would you try to phrase this as an optimization problem with like some variables, constraints, some objectives? What variables might you use? Yeah. The what time? Wait times. Okay, let's see. And what do you mean by that? Right? Okay, so he's suggesting maybe you have for every job a variable called waiting time of I. This is basically the time at which job I gets scheduled. Sure. Yeah. So in this language, how do you express the problem? So this is a fine variable, right? Like you could say, okay, fine. This is. How would you express the? Do you have answered to this question, or did you have a different? Yeah. Okay.
Minimize the sum of all the wait times for all the jobs.
Yeah, so why would that capture the objective that you want? Right, so you're saying, oh, okay, so sum of, so you're going to minimize sum over I with that I. So the sum is a bad quantity, right? Like you don't care so much about the sum of the wait times because, I mean, in some sense, you could. All you want is to finish. Is for every machine to finish before time t, right? And that's the quantity you want to minimize. You don't care so much about when the job started or how long you had to wait. Intuitively, they are connected. Right? So intuitively, they are connected, but there's no formal relationship between the t and the sum of the wait time. It's very instance dependent.
Are all the machines the same?
Yeah, they're identical. Yeah. So the length I is so no matter which machine you assign a job I to, it always takes Li time. Yeah, so that's a good point. Okay, so there's scheduling literature, there's all kinds of ones. Unrelated machines. Yeah. So yeah.
You could find the minimum over all I, or rather find the maximum over all I at the waiting time plus the actual length of the job and minimize that maximum.
Yeah, so if you have these as your variables, then the objective would be not this, but it would be something like minimize the max over all jobs I of the waiting time of I plus the length of I. Because this is the time at which it would actually end. Okay, and this is what you want to minimize. Right? So this is fine as far as the variables go and the objective. Okay? But yeah, so what are the constraints? Because so this is why so when you're thinking of phrasing a problem as an optimization problem, the way you should be thinking is I'm given these variables and I'm given the constraints and the objective, and I know nothing about the problem domain. Okay, and now this just becomes a math problem, right? So and any solution to this is supposed to give me a schedule. Okay, so if you want to ensure that, how would you write constraints that these W's should satisfy? So is what I said clear? Like what I'm saying is the point of reducing a problem to optimization is that you come up with an optimization formulation, then somebody who just sees the optimization formulation should be able to deduce a solution to the original problem without knowing anything about uh, where this problem arose from. They may not know anything about scheduling, okay? But they will produce a solution. From that, you should be able to deduce. But if your problem was just phrased like this, right? Your variables are Wi, and W's could be anything for all you know. Then if I had jobs like of lengths 1, 2, 5, and if I had let's have one more. So these are the chains, and let's say M was 3. Now these are L1, L2. Okay. Now I could hypothetically, somebody who's solving this optimization problem could say, okay, I want to set W1 equals W2 equals all of these equals. And this would achieve a reasonably small objective value, right? So, but of course, you know intuitively that this is not possible. So how do you add constraints so that you prevent a solution like this? Yeah.
You probably want another variable that represents all of the jobs assigned to a particular machine.
So that would be a set variable. Okay. So you want to so then these W's no longer come into play. So he's saying, okay, so you want to assign variables x sub 1, x sub 2 to x sub m, where these are set variables. Like each variable takes values that are like subsets of 1 through n. And these are your variables. So this is fine, except that, I mean, would you expect any reasonable optimizer to be able to solve over set variables? Right? It seems tricky, right? Because you have to try out all subsets. So there are many ways of phrasing a problem as optimization, but some are more reasonable than others. Okay, so one of the something of an art is how do you phrase a problem in a reasonable optimization? So yeah, but the set variable does bring about an interesting aspect, right? Like it says perhaps you've got to have some notion of this, right? Like you've got to have some notion of what machine job is assigned to, okay? Or what jobs are assigned to one machine, something like that. So maybe you could expand on these and say that I have x, instead of just x1 through xn, okay, suppose I have xij that denotes is job j assigned to machine. So this is now a Boolean variable. Okay, job j assigned to machine. So this would be a more realistic way of implementing this idea. Because clearly having set variables seems a little unlikely that you'll be able to optimize those directly. Right? So instead of having a set variable, just think of expanding each of these x into like a bunch of n variables that basically says, oh, is this job on this machine? Okay. So this is more reasonable. Right? You agree? Because these are not just booleans, right? But of course, so even here you need some constraint. But yeah, so this is at least xij and this boolean. Okay. So this is one way to assign variables. Alright, so, but if you have, okay, so I guess we have, we stopped thinking about these as variables because it seems like it's hard to impose constraints so that you avoid cases like this. Okay, so let's, at least I don't know how to easily impose constraints using those kind of variables. So let's try with these variables, right? So these look like reasonable ones. Now, if you want to, so let's, so variables are xij, just like 0, 1. So the domain for each of these variables is 0, 1, and is 1 if and only if job I, so job j is assigned to. Okay, and so this is another sanity check when you're trying to come up with optimization problems. Usually your set of variables must give you a way of reading off a solution. Okay? Like, so in the sense that, suppose I gave you a bunch of numbers xij, the 0, 1s. And from this set, you should be able to come up with an assignment of jobs to machines. And in this case, you can do that. Right? Because if xij is 1, then I know that job j is assigned to machine. Now you've got to make sure that job j is not assigned to multiple machines. But that you can impose as a constraint. And that's the kind of a thing we want to do. Okay, so one of the sanity checks is that is that the variable or an assignment to the variable must let you read off a solution to the problem. And this is one of the important things. So this is often what you would want from an optimization formulation. And okay, so if these are the variables, so what are the constraints? Yeah, maybe.
For every job J, there can only be one xij.
Okay.
Job N assigned to a machine.
Yeah, so we want every job to be assigned to one machine. So for all jobs, sum over I equals 1. So it must be assigned to precisely 1 to square root equal. So this is that. And any other constraints you might want to add? Yeah.
All machines I.
Yeah.
The sum should be less than t. Something. No, but
Yeah. Well,
We need to include the length of it. The product of length
yeah. So what you would like to have is for right. So for all machines I, okay, the yeah. So intuitively, what you want is total length of jobs assigned is less than or equal to the speed, right? So how do you capture this as a function?
Having it where the product of LJ and XYJ
Uh-huh.
and sum over this.
Yeah, exactly. Right. So you would say is sum over j Lj times xij. This is less than equal to, because xij is a 0-1 thing. So it'll be 0 for every job. I mean, if job I was not assigned to the machine, if job j was not assigned to the machine, and it'll be 1 otherwise. So this exactly captures the total length of jobs to machine I. So this is now a reasonable optimization problem. And your goal is, of course, to minimize speed. Okay, so objective is to minimize. So technically speaking, t is also a variable, and t is a variable is the time, and you want to minimize this t subject to, and this takes any integer. Okay. So this is one way you can write this job scheduling problem as an optimization. The point is that you chose variables carefully so that they allow you to like read off a solution. And yeah, and you have these constraints which say this. And right, so now the key point is that suppose somebody had no idea that you were trying to solve a scheduling problem. But you just gave them this optimization problem, okay, where let's do it for this, okay, for this example. So you just told them, so x, so you have variables that correspond to x ij, where 1 less than equal to I less than or equal to 3, and 1 less than so these are all your variables. So you have 18 variables, and you just tell them that there's a bunch of constraints here, which is like x x11 plus 1 plus 3 1 equal to 1. And the same thing when the 1 is replaced by 2, 3, 4, 5, 6. Okay, so let me just write this as for and you gave them this other constraints also. Okay, and you just said, yeah, minimize the speed subject to just the constraints, right? So now the person who gets this is just getting optimization problem. So they don't have to know anything about scheduling. So you just have these xij supposed to be Boolean numbers, and this is, and let's say they solve it by whatever means they have. Okay, yeah.
With the length, well, outer length, and
Yeah, that's also included. Yeah, I just don't have space. I don't know. Maybe, so this is a different type, but I don't know how to add it. Maybe it's not so hard. Yeah. Okay, so, okay, so, yeah, let me do this. Right? Okay, so yeah, and you added a constraint also that says, essentially that, yeah, maybe I'll write the whole thing. Okay, so suppose somebody just told you have variables xij where one has the I and for all j you have x1 and you have for all I x1 I times, let's say my job lengths were known, right? So the job lengths were 1, 1, 2, 3, 5, 3. Okay. So times 1 oh, sorry, wasn't it 1, 2? Yeah, 1, 2, 3. That's into the L. Okay, so L is some variable. And you have such a constraint for every I. So here there are 6 constraints. And here there are 3 constraints like this for every I. And you want to minimize it. And of course you know that xij belongs to 0, 1 and L belongs to integers. Okay. So your variables are those guys, and and these are the constraints they should test. So suppose suppose you have an oracle that can solve any optimization problem. Okay. So you just give the oracle this set of equations and this set of constraints, and you solve this optimization problem. Now you can observe that any solution to this can be interpreted as a solution to it. Right? So the oracle doesn't have to know anything about your scheduling problem. So they don't have to know that you're doing scheduling. So that is the key when you're thinking about optimization. That when you phrase a problem as optimization, you assume that there is a black box that solves this optimization problem without knowing anything about the context where it came from. So students often miss this, so even though it seems like an obvious point, I'm stressing this. Yeah.
Are there only possible constraints, like linear combinations with equals or less than equals?
What else do you want?
I'm just wondering, like, what is equivalent?
I mean, so it depends on the oracle, but very often, yes, those are how most optimization programs would take. Yeah. So and it's hard to find things where you cannot write it that way. So usually you can somehow massage the problems to be written that way. Yeah. All right. So this is, yeah, so this as I was saying is the key thing. But solving this black box optimization problem should tell you something. Alright, so let's see a different example. Okay, so this is again our favorite problem, right? Matching. You have a bipartite graph, and you have S and you have T. Okay, and so you have weights on edges, and this is what's given to you. You want to find a matching so that sum of, let's say this is for now a complete graph. Okay, like for every ij there is some weight, and you can assign every I to any j. Okay, and you want to find an assignment sigma. Assignment I comma sigma I. To n is such that sum over I, the weight of I sigma of I is not. This almost looks like an optimization problem. I mean, already, because I have some objective function and I have something. But of course, the sigma i's are strange variables, right? So, in some sense, if you could say optimize over sigma being a permutation, okay, of optimize over all permutation sigma of this thing, okay, then this would exactly capture the problem. So this is similar to the solution he suggested before, right? Like your variable is like a set variable. Right? So this is now a permutation variable. But these are tricky to optimize. Okay, so let's can you phrase this as a problem where you still have, let's say, Boolean variables, and you phrase it as a optimization problem like you did before. So what kind of Boolean variables would you introduce?
So it's similar to the previous problem, for example, you can say x I j means the I is connected to j.
Excellent. Yeah. So this is it's very similar to the previous problem because like it's like saying, oh, the left side was job, the right side was machine. So you have let's say x I j is a variable that is this is belongs to 0, 1. That is 1. If I is assigned to match with j. Okay. I sigma of I is j. So you have something like this, and it is 0 otherwise. Now, if you have a problem like this, okay, so if you have variables like this, so now what would be the constraints you would have? Anybody else? It's a slight difference between the previous problem and this one. So let's try to see if somebody will catch. Yeah.
So you want all children to be assigned exactly one gift and all gifts assigned to exactly one children, right?
Yeah, so that's the only mild twist here is that there's no like minimization of L kind of thing. Here you have every child is assigned precisely one gift, and furthermore every gift is assigned precisely one child. That was not there in escape problem. So what you have is that for all I and S, you have sum over j x I j equal to 1 and j. rho j have sum over I of x I j. These look very similar, but summation in the C side. Alright, so here the j is fixed, here the I is fixed. So that's so these are the constraints you have. And now, what is your objective? Whoa. So any other constraints you can think of? Or fine for now. So yeah, okay. So I mean, yeah, let's stick with this. I think it's fine. So now, yeah. So what about the objective? What is the objective?
Kind of already written on the right side, it's to maximize W I sigma I.
Right. But you don't know sigma I. So how would you write that using these variables?
We just need a new variable that captures the weight, because Xij just captures if there's a connection, but doesn't incorporate the weight. You want the objective to maximize the weight.
Right. So ideally, what you want to say is sum over all edges ij for which xij equals 1. Right? Because xij was 1 only if j was sigma pi. That's how we define that xij. Right? So it's a variable that is 1 if I is matched to j and 0 otherwise. So a solution, a valid solution to this would be something like this is 1, this is 0, this is 0. And maybe this is 1, this is 0, this is 0. And so on. Right? So, yeah.
We could just sum over all i's and j's multiplying xij.
Exactly. Yeah. So you can just say the sum over all edges, okay, xij times wij. And this captures what you wanted, because xij is 1 only if I was matched to j. In that case, you want to get wij into your sum. Okay? And otherwise, xij was 0, so whatever the coefficient was, it doesn't matter. Okay? So this is exactly how you would capture this objective. Okay? I mean, this, or rather this particular. So yeah, so this is a clean way of stating this. That's one over all pair signs. So this is again, you should verify that now if someone gave you a bunch of equations of this kind without telling you anything about matching or scheduling, whatever, you will be able to use a solution to this to come up with an instance. To like an actual assignment. So this is yeah. So this is again easy. So this matching word is an example that's rather similar. Okay, so now let's okay. Actually, maybe I'll wait a little bit. So this is clear. Maybe this. Yeah.
What if for like a open optimization problem you have an exponential number of constraints or variables?
We will just see an example. So yeah, I mean that's a yeah. Typically you can't solve them, but in some cases you can. Just to short out. Yeah. So yeah, so sometimes you may not have like a clean way of formulating, and let's take shortest path. Okay, we know and love shortest path. We can all solve the problem effectively. But suppose I wanted to phrase it as an optimization. Okay. Like, so what variables would you choose and what constraints would you have? Okay, so you have given, let's assume the graph is, you like directed or undirected? I didn't really know. Let's assume undirected. So you have some undirected graph with weights. WE. You're given a source and given S and weighted. So, how would you phrase this as an optimization problem? Well, I mean, again, when someone asks you this, you should be asking yourself three questions, right? Like, what are the variables? What are the constraints? What is the objective? Right? So those are the three things you have to think about. So, yeah. So, variables. So, what would you say are the three things?
One method can be, for example, XIJ, which denotes whether notify or multi are connected as well.
But that you know from the graph, right? That need not really be a variable. So variables should be, think of them as things you should optimize for.
Like if we have such a variable like how far it is, by the weight of the edge, we can optimize.
Right, so your intuitive idea is, okay, so maybe I want to have variables corresponding to edges. And somehow, but yeah, so you can actually make that formal, right? You can say, maybe I have variables corresponding to edges, and I want a one only if it's an edge on the shortest path, okay, on the path I want to find. So that's something totally reasonable to do, right? So for every edge xe is 1 if e is on this candidate shortest path. And 0 otherwise. So if, yeah, in some sense, if E is on my path and 0 otherwise. And this could be, yeah, this could be a valid way of writing short path. So, I mean, these could be candidate set of variables. So now, so the variables that have been defined, and one of the motivations for writing these variables is that the objective is now clear. Okay, so the objective is now minimize sum over all e x e times w. So this is exactly the idea that you also mentioned. Right? Like you just so if w if x e is 0, means it's not an edge on your candidate path. Then it's 0. So that's what we have here. So now comes the tricky part. So what are the constraints? So somehow we want any feasible solution that we have to actually correspond to some path, right? I mean, you don't want, I mean, for example, if this your S is your T, you don't want this edge to have an xc value 0, this x to have 1, this is 0, this is 0, this is 1, this is 0, this is 1. So this could be, this is not a valid solution because the ones don't give you a path going from S to T. Okay, so right, so you've got to write constraints that weed out solutions of this kind. All right, so somebody had a.
Maybe you could describe exactly what you just said, so maybe every edge connects to another edge, and at some point, S is connected to that, and T is connected to that.
Right, so this is a clean way of stating it. Right? What he's saying is, what is a path? Right? A path is a contiguous set of one edge connecting to another edge, this edge connecting to another edge, and so on. Okay? Now, how do you formalize such a such a thing? Right? So, makes you wonder. Maybe life would have been easier if I had a directed graph, or it should be making you wonder, right? Because if you had a directed graph, you could have said, "Hey, I have one edge coming in, one edge going out." Okay, but yeah, now maybe you're thinking maybe it chose undirected by this. Yeah, okay, so yeah, no, but it does make the problem a little simpler if you're undirected. But of course, you can always make any undirected graph directed by adding two edges. So you could do that. So you could always say, I have two variables per edge, one in the forward direction, one in the backward direction. Okay, one in like going in and one going out. Okay. So you could have two oriented edges. So that's one idea. Any other ideas? Yeah.
We can do a connection matrix.
Okay.
And I want to use the fact that raise the connection matrix to k power will give you whether 2 points are connected in the path of that k. And then if we sum k from 1 to n minus 1, and if that's greater than 0, then it's
Right. But now how do you view the connection matrix? I mean, how do you write this as a constraint?
the variables are still x, j,
Okay.
and the constraint is the sum of x as a matrix raised to k power, and sum over k from 1 to n minus 1, and sum all the x st elements, and the constraint should be greater than 0.
Okay. So what he said is a correct solution, but I don't know if I have the time to explain this. But actually, did people follow what he was saying? Okay. So what he said is it's a very interesting solution. Maybe I'll write it. Okay, so it's so you have these variables xij. Think of writing them down as a matrix capital X. Okay? So it's x is ij and is xij. Okay? And what you can verify is that x squared, if you view this, it has variables of the form. The ijth or rather, yeah, the ijth entry of x squared would be something like xi sum over all k, xik times xk. Okay. And so this corresponds to a path of length 2. Okay. And so this would be, so the ijth entry would be 1 only if there existed a k such that xij times xjk was 1. Okay, so you can actually do this. You can do this for any k, and you can just say that x superscript x to the power of r is a matrix where the ijth entry is 1 only if there's an r length path not necessarily a path actually, you can take an edge and come back and so forth, but yeah, there's an R length, it's called a walk, between I and j. Okay? And then you could have a constraint that says sum over R going from 1 to n x to the R. You look at this big matrix, okay, and you have the SPth element of that should be bigger than equal to 1. Because using the edges chosen, you must be able to find a path from S to T. Okay. So this is great, except that this is a degree n constraint because x to the r is an rth degree polynomial. So this is a perfectly valid solution. It's again, it's one of these things where if you have high degree equations, optimization becomes difficult. Okay, so this is fine, but this is still tricky. So this is one solution. The other solution that we got is maybe move to a directed graph. And have a constraint that in degree equals R degree. So this was the other idea. Okay. So yeah, so these are two ideas. This is a bit more complicated. Okay. But it's perfectly fine. And but note that all of these are formulations using the same set of variables. Okay. It's just that the set of constraints are different. So I haven't explained what these constraints are yet. I mean, we have a rough idea. But let me tell you a different set of constraints that, and then you should be able to see where I'm going with this. Okay, so which is that the constraint I want to add is I want to take any set of vertices that contain S and do not contain P. Okay? For any capital S that such that capital S is in capital S and P not in capital S. I want to say that at least one of the edges xij that so for all S satisfying capital S, small s in capital S, not in capital S, one of the edges in the cut is chosen. Okay, so this is something you could write, right? Because for every S, you know that which edges cross the cut. For every choice of capital S, you know that which edges exactly cross the cut, and you just say sum over all edges E belonging to cut of S x sub E is bigger than or equal to 1. Okay, and this must be a valid solution. This must give you a path. I mean, so if I now look at the set of all xp's that are 1, maybe there's some, maybe these are the guys that are 1, and maybe t is like this. So these, think of them as set of all xp's that were 1 in some candidate solution. Now this cannot be a candidate solution because now you have a set of vertices is that no edge going out of this is selected. So these are my 1 edges, and there are other 0 edges. Okay, so there are other 0 edges. So any set of edges where there is no path bits from S to T is ruled out by inequality. Now, of course, this could place more. This could actually have. This would allow solutions of this kind. Right? So you can have more than necessary, and a bunch of zeros for all the other edges. So you could actually have more than necessary, but I claim that that's not needed. I mean, that's not a problem. Do you guys see why? And so the point is that if you optimize, you will never end up with a solution where some unnecessary things are set to 1. Because you could have removed that edge and your cost will become better. Okay? So you can think of solving this optimization problem. The optimal solution will actually still be a path. Okay? Yeah, unless weights are negative.
What happens if there's still no actual connection? We selected a bunch of edges and then going to T, there's no connection from that edge to the rest of the edges.
Yeah, so let's say you're in this situation. Let's say you're saying that there's S, there's 1s, and there's one edge from T that is here, but there's no edges rest of the graph. So now this is a cut with no edges crossing it.
Yeah, and so maybe there's another vertex inside of the S bubble that goes to T, but it's not actually connected to the vertices.
In this picture, you're saying that this guy, right? Okay, but then I exclude this vertex and say this is now right. So this is why you need this constraint for every set that satisfies this constraint. So for all S satisfying S and S and T in S, you have it. That's a great point, right? So what he said is, if I have this for one set, maybe I could say, okay, this could have been an edge. But now I'm just saying, okay, I exclude this vertex from that bubble, and this is no longer in the cut. So I just take in this graph with just one edges, I just take the connected component of S, and I use this argument for that. So yeah, so think about this a little bit. So in fact, this turns out to be a nice connection to flows and cuts. So this formulation is exactly like saying that the minimum cut going between S and T in the set of 1 edges is at least 1. Okay, and this moving to a directed graph and having a constraint that in degree equals out degree is exactly like saying there's a flow of at least 1. Okay? And both are equivalent to saying there's a path. And so it turns out that there's this nice connection. So this is why you have two formulations, and both are essentially saying that this formulation is saying that there's a flow of 1, and at least 1. That formulation is saying that there's no cut. So that's the nice thing here. But note that this formulation is small, and this goes to the point that he made, is that here you just have this for every vertex in degree equals out degree. So you just have like n constraints. But in this formulation you have exponentially many constraints. You have this constraint for all x. So that's so for the same problem you could have a clever formulation that is polynomial size. More naive formulation that's exponential size. Or you can have a formulation like he said where the degree is cubed. It's still polynomial size, but maybe the degree is cubed. So come back to this.